So in this example, we're going to review parametric equations, and we're also going to practice our notation for our vector value functions, and we're going to remind ourselves how to graph some things. So this will be fun. Okay, so let's start off with this equation right here. So 2x plus 3y equals 6 from negative 3, 4 to 6, negative 2. Okay, so again, the easiest way to do these is to let x be t. But if you're going to do that, you have to solve the equation for y in terms of x. So you'll have to say, okay, so let me see this, 3y equals 6 minus 2x. So y would be equal to 6 minus 2x all divided by 3. All right, so then when I go to the parametric form, then it would be y equals, well, 6 divided by 3 is 2. So 2 minus 2/3 t. All right, now where's t restricted from? Because part of parametric functions means you have to have a restriction for your domain, or you have to state that there is no restriction. So we're going from negative 3, 4. So if x is t, that means that we're going from negative 3 to positive 6. So there would be the parametric form of this line segment. Let's face it, it's a line segment. All right, so then if we're going to write it in vector form, it'd be t comma 2 minus 2/3 t. And again, part of writing it in vector form will be to have the domain restriction if there is one. All right, so let's look at a graph. We have our coordinate axes. So my paper bunched up on me. There we go. All right, so we have the y and the x-axis, and we all know what this looks like. I mean, this is a line, right? So it's going through 1, 2, 3, 3. Oh, sorry, no, it's going through 2. My fault, 2. For some reason, I just looked down and saw 3 on my paper. All right, so it's 2. So 2, and then we're going to take away 2/3. So that's rise over run. Down 2 over 1, 2, 3. There's the 3, right? And we're going to go from negative 3, 4, which would be up here, down through 6, negative 2, which is, let's see, 1, 2, 3, 4, 5, 6, negative 1, 2, be down here. And we have to have motion on it. So we're going from this point down to that point. So we put arrows on it. All right, now let's do it again. So y is equal to e to the x. That's an exponential function from 0, 1 to the natural log of 5, 5. Again, the easiest way to rewrite this is x equals t, y equals e to the t. And we would say that t is restricted from 0 to the natural log of 5. So to write it in vector form, vector value function form, we would put t comma e to the t, and then we would still say the same restriction. So you can see that parametric and vector value functions are very closely related to each other. Right, so again, let me draw some axes in here. All right, well, we know that at 0, it should be at 1, which is right here. And then it's going to move its way to the natural log of 5, 5, which is over here. So I'm going to pretend that's 5 and say that's the natural log of 5. So, and it moves that direction. All right, now, what about this? Okay, so this is an exception to our x equals t rule. We don't usually use x equals t for certain types of functions, 2 particular functions. So I'm going to write this in pink just to kind of warn us. x equals t is not used with what this is, which is circles, nor ellipses. We learned about those when we learned parametric functions, right? So that's an exception to our handy-dandy rule. So for ellipses and circles, we do not use the x equals t, which is what these two are. This is a circle, this is an ellipse. Okay, so let's think about this. This was a circle with radius 1 and it was centered at the origin. So I can tell the center is 0, 0, the radius is 3. Real quick, well, how do I know that? Let me just write it in down here briefly. Um, Actually, I'm gonna write it down here. I'm gonna have some space. For a circle, the radius is r and the center is hk. The format is x minus h squared plus y minus k squared equals r squared. You should have learned that somewhere along the way in algebra class, in geometry class, in algebra 2, pre-calculus, right? That is the standard form for a circle. So that's how I know when I look at this. I can see there's nothing with those x's and x and y, so I know that the center is 0, and I can tell that r squared is 9, therefore r is 3. All right. Then we learned in Calc 2 or pre-calc how to write those. They are x equals 3. Oh, and then look very carefully. Clockwise versus counterclockwise. So we learned that too. So since it's going clockwise, we actually use sine here and y equals 3 cosine here. So when we do parametrics for those, it's, if you want clockwise, it's sine for the x, cosine for the y. When we want counterclockwise, we reverse it, which is why your unit circle that you learned about in pre-calculus always had x as the cosine, y as the sine, because you move around the unit circle in a counterclockwise direction. All right, now what are we restricting from? We're only going around this once. So you can see it says we're going around once right here. And that means that our domain is going to be restricted from 0 to 2 pi. All right, so in vector value form, we just write it with vector notation. So you get 3 sine t, 3 cosine t, 0 is less than or equal to t, which is less than or equal to 2 pi. Okay, so when I draw the circle, so I have my coordinate axes right here. I'm going to draw the circle. I'm not actually going to draw it in a clockwise direction because I'm not good at drawing circles in a clockwise direction. So it's going this way. It's going clockwise. All right, so now let's look at this ellipse here. Now I can tell it's an ellipse because it's got the x squared plus y squared, right? It's the same form, sort of, as the circle. However, it has these numbers in front, which that's no good. Okay, so that leads us to reminding ourselves what the standard form for an ellipse is. So an ellipse with center hk is written like this. It's x minus h squared over a squared plus y minus k squared over b squared equals 1. Where a and positive a would be the vertices in the x direction, and b and negative b would be the vertices in the y direction. It can get a little more complicated than that, actually, significantly more, but we're just going to leave it at that, right? So that is the standard form for the ellipse. Okay, so how does that help me? Well, if I look, I can see it's all equal to 225. So what I'm going to do is I'm going to divide everything by 225. I'm just going to do it down here because I don't have room. All right, so 9 over 225. Here, I found it in Desmos for you. So 9 over 225 is 1 over 25. And while I'm here, 25 divided by 225 is 1/9. Okay, so let me go back and write those. Right, so I can tell that it has vertices in of plus and minus 5. So if you think about this, I can draw the picture first. Do it a little out of order on this one. All right, so I know that it's going through 5 and -5 for the x direction. And I know it's going through 3 and -3 for the y direction. So it's going like this. It's an oval shape. And this time we're going counterclockwise. Okay, so we're going this direction, which is the way I drew it. All right, so at that point you have to remind yourself how to do these. And the answer is they work very similar to circles because they're closely related. So you just say, okay, since I'm going counterclockwise, this is cosine and sine. If it was a circle, it would be the same number in front, 5 and 5, 3 and 3, and so on. But because this is an ellipse, it's farther out in the x direction, this particular one is. So I put the 5 here, and I put the 3 here. The vertices values, right? A would be your x vertices value, vertex value, and the B, which is 3, would be the y vertex value. And those become the coefficients in front of your cosine and sine. Now, if we're going to traverse this only once, just like we did on the last one, that means that, again, we're going to go from 0 to 2 pi. Don't forget that if you're going clockwise, you use sine for your x, cosine for your y. And if you're going the opposite way, counterclockwise, you use cosine then sine. Let me put these into Desmos real quick just to show you that this is the case. As a matter of fact, I figured I'll show you all of them. So here's the line. So you can see that it goes from up there to down there. And I define it in Desmos the same way that we define it on the paper, right? T comma 2 minus 3t. I just added this little bit of code so you could see the motion, because otherwise you can't really see it. So that's the line. There's the exponential curve, moving just like we said it would, right, up to that piece. All right, now here's the circle. Here's what we're here for. So I define this with 3 sine t, 3 cosine t, and you can see that it is moving in a clockwise direction. We learned that in Calc 2, that it moves in a clockwise direction if we do that. All right, now what about our ellipse? There it is. And you can see that it's moving in a counterclockwise direction because I defined it with cosine first in the x position, then sine in the y position, and that will make it move in an elliptical fashion. And you can see that the x vertices, if you will, are 5 and -5, and the y vertices are 3 and -3, just like we expect from the function. So all we have yet to do is to fill this up. It'd be 5 cosine of t, 3 sine t, from 0 is less than or equal to t, which is less than or equal to 2 pi. All right. So there's a bit of review on how to do parametric equations, how to do circles and ellipses, how to get them to circles and ellipses to move in the orientation you want, clockwise or counterclockwise, and a little review of some algebra down here.